Recently, satellite images taken of the Dalian shipyard went viral online. The images show several deck modules in the dock, with 4 parallel tracks outlining the design for electromagnetic catapults. Soon, CG enthusiasts quickly created 3D models, paired with dramatic background music and narration, showing a world's first super aircraft carrier. The carrier, dubbed the Type 004, is said to be 350 meters long, displacing 120,000 tons, with 96 aircraft, 4 electromagnetic catapults, and a thorium molten salt reactor, and advanced weapons systems like laser guns and railguns. It is also claimed to have the ability to launch aircraft every 30 seconds and strike targets globally. But how realistic are these features, and which of them are still in the concept stage, and which are severely overestimated or completely imagined? One feature almost always included in the specifications for the Type 004 is the 4 electromagnetic catapults, which promise to launch aircraft every 30 seconds, giving the carrier a rapid deployment capability. But there's a critical issue: the power requirement. While electromagnetic catapults appear to be a simple, track-based launch system, they're actually energy-intensive devices. Instead of using gunpowder to launch an aircraft, they rely purely on electricity to accelerate a 30-ton jet from 0 to 300 kilometers per hour in just 2 seconds. The big question is, where will the power come from? Can the system store and release it quickly enough? Can it handle the immense demands? To launch a 30-ton jet to 300 kilometers per hour, the actual power requirement is about 150 megajoules, or 42 kilowatt hours. This amounts to power that could supply a typical household for 4 days. But it must be released within 2 seconds, meaning the power needed is 75 megawatts. If all 4 catapults are in use at the same time, the total power requirement would be 300 megawatts. For comparison, a nuclear-powered aircraft carrier typically has a total power output of about 600 megawatts, meaning half of the power would be consumed by the catapults alone. Now, if you also want to equip the carrier with laser guns, railguns, radar systems, and communication systems, there won't be enough power left. In reality, whether the power comes from a nuclear reactor or medium-voltage direct current, aircraft carriers must rely on intermediate energy storage systems. The U.S. Navy's Ford-class carriers use flywheel energy storage, which can release tens of megawatts within 2 seconds. However, this system is large, wears out quickly, and has high maintenance costs and a significant failure rate. According to U.S. Navy test data, the Ford-class electromagnetic catapult system experiences 1 failure for every 400 launches, far below the design target of 4,100 launches without failure. This leads to unstable mission rhythms, crew fatigue, and chaotic scheduling. China's Fujian carrier reportedly uses supercapacitors for energy storage. While supercapacitors have a much lower energy density than flywheels, they offer more stable charging and discharging cycles and have a longer lifespan. The issue is that to store 150 megajoules for every catapult launch, supercapacitors would need to occupy much more space. If the Type 004 were to be equipped with 4 catapults, the energy storage system would weigh over 500 tons and take up several thousand cubic meters of space. The system would also require cooling systems, transformers, control panels, and heat dissipation channels, making it one of the most complex engineering systems on board. More importantly, all energy systems must face a crucial reality. If one catapult fails, can the remaining catapults still operate at full capacity? Is there enough redundancy to ensure continuous power? Why does China's Type 004 need 4 catapults? The most reasonable explanation is not to outdo the U.S. military, but to ensure redundancy. If one catapult fails, the other 3 can maintain the operational rhythm. In high-intensity combat readiness, the catapults can be rotated to reduce system fatigue. Additionally, placing the catapults at the front, middle, and rear of the deck can help distribute the scheduling pressure. 120,000 tons, the ultimate challenge in carrier design. When a short video claims that the Type 004 will reach 120,000 tons, far surpassing the U.S. Ford class. But the key questions from an engineering perspective are, how will you build it? Where will it be built? And what materials will be used? The larger the aircraft carrier's tonnage, the challenges don't increase linearly, but exponentially. Moving from 100,000 tons to 120,000 tons marks the boundary between engineering limits and physical reality. It is widely acknowledged that the Type 004 will be built at the Dalian shipyard, which has the largest dry dock, measuring about 350 meters long, 70 meters wide, and 14 meters deep. To compare, the U.S. Ford-class carrier is 337 meters long, with a waterline width of 40.9 6.8 meters. The flight deck's maximum width is 78 meters, and its full displacement is about 110,000 tons. The Type 004, however, needs to reach 120,000 tons, meaning every dimension must be increased. The hull will need to be longer, wider, deeper, and the modules heavier and more complex. Here's the problem. The dry dock's width is only 70 meters, but the flight deck needs to be 83 meters wide. So where does China plan to build the flight deck? If the carrier truly reaches 340 meters in length and 75 meters in waterline width, the available space in the dry dock would be almost zero, leaving no room for welding, lifting, or personnel operations. The depth of the ship's hull needs to be at least 12 meters, but the Bohai Bay has minimal tidal variation, meaning the window for launching large carriers is largely limited. It would either depend on favorable weather or require significant modifications to the dry dock. An aircraft carrier must withstand numerous stresses, launching and landing dozens of aircraft, ensuring wind and wave impacts, weapon recoil, jet vibrations during takeoff, and frequent weight changes. The hull strength depends on the keel and longitudinal structure. The issue is that once the ship exceeds 330 meters in length and 100,000 tons in displacement, the structural stresses no longer increase linearly. Wave bending moments increase dramatically. A force equivalent to several billion Newton meters can affect the hull in 6-meter waves. If the parts of the hull sink or lift, it can cause the flight deck to tilt, affecting the precision of the catapult tracks. The strength of the keel material, the number of connection points, and the density of the structural supports all need to be massively upgraded. The shift from the U.S. Navy's Nimitz class to the Ford-class carrier was primarily a matter of fine-tuning tonnage and design philosophy. Behind the shift was the transition using HY80 steel to stronger HY100 steel, a high-strength material that only a few countries currently know how to process. China's Fujian carrier, however, jumps directly from an 80,000-ton design to 120,000 tons, with no intermediate-scale hull engineering to serve as a testing platform. This leap is an unrealistic fantasy. Dalian Shipyard's equipment limitations. The largest lifting equipment at Dalian Shipyard consists of two 900-ton gantry cranes. The issue is that the heaviest sections of the Ford-class carrier exceed 1,100 tons. If the Type 004 actually reaches 120,000 tons, each individual module would weigh more than 1,500 tons. So what happens if they can't lift these modules? They will need to be broken down into smaller sections, then assembled in the dock. This results in more welding seams, higher risk of errors accumulating, and more complicated structural calibrations. Even a slight welding defect can cause fatigue or cracks in the structure over time. For example, the UK's HMS Queen Elizabeth carrier had a slight welding deviation in its hangar module, only a few millimeters, but it caused a misalignment for the entire hull's centerline, requiring the section to be removed and rebuilt. China will face a dilemma in the early stages of the Type 004's construction. The challenge of an 83-meter flight deck. One short video claims the Type 004's flight deck will be 83 meters wide, 5 meters more than the Ford-class carrier. The immediate response from engineers is, can the structure support this? The flight deck is a massive cantilever structure that must withstand the impact force of aircraft taking off and landing, which can be tens of tons per second. The distribution of structural stress due to additional loads like aircraft, elevators, and catapult tracks. The density, strength, and connection methods of the beams supporting the deck below. Here's the problem. For every additional meter in width, the complexity of the transverse structure increases exponentially. If the beam spacing stays the same, additional beams will be required, which will reduce the space available for below-deck compartments. If no extra beams are added, heavier and thicker materials will be needed, which will raise the ship's center of gravity and reduce stability. The width of the Ford-class carrier's deck is the result of decades of testing and operational excellence. It wasn't a matter of doing what's possible, but rather it was the optimal solution within the limits of the structure. To increase the deck width by another 5 meters, the entire structural system of the carrier would need to be re-engineered, but right now there isn't even a testing platform to verify the design. 120,000 tons. Not just 20,000 more tons, but a whole new technological dimension. Increasing the displacement from 100,000 tons to 120,000 tons is not just about adding 20,000 more tons. It introduces an entirely new set of technical challenges. This change means that the dry dock will need to be expanded, the keel must be redesigned, materials must be upgraded, lifting equipment may not be sufficient, and every engineering process will enter uncharted territory. Thorium molten salt reactor, from laboratory to the oceans. Among the most futuristic claims about the Type 004 is the idea that it will be equipped with a thorium molten salt reactor. The claims are that it will operate for 50 years without refueling, generate power with no waste, and can automatically solidify to stop the reactor, making it safe and environmentally friendly. But where has a thorium molten salt reactor ever been used on a ship? The answer is nowhere. China is indeed developing thorium molten salt reactors. The world's first was completed in Wuwei, Gansu in 2021, with a power output of just 2 megawatts. While this is a groundbreaking achievement for an experimental reactor, moving from a 2-megawatt reactor to a 200-megawatt reactor suitable for naval use is like going from a paper airplane to a space station's transfer port. Nuclear reactors on military ships must meet several extreme requirements. First is high power density. Only a few cubic meters needs to produce hundreds of megawatts of thermal power. 2. Compact design. The reactor, cooling system, shielding layers, and turbine generator must all fit into the midsection of the ship. 3. It must be resistant to movement, shocks, and corrosion, operating smoothly even while facing waves, impacts, and tilting on the high seas. The U.S. Navy achieved 110,000 tons with decades of experience, thousands of tests, and a fully supported industrial and design system. Meanwhile, on platforms like China's TikTok and military blogs, these massive undertakings are often reduced to a CG animation, a few dramatic lines, and a series of precise but fictional parameters. While molten salt reactors are theoretically safer, they face 2 major practical challenges. First, they're liquid-based. On a moving ship, the molten salt in the core will shift, disrupting the neutron flux and causing unstable reactor power, potentially leading to an automatic shutdown. 2. They require extremely high temperatures. Operating at 700 degrees Celsius, the material requirements are severe, and designing a cooling system is even more challenging. If the cooling system fails, restarting the reactor would be extremely costly. Right now, no military ship, not even a submarine, has ever used a molten salt reactor. China itself has not advanced to a commercial verification reactor in the civilian sector. Can such a system realistically be installed on the Type 004 aircraft carrier? A more pressing issue is that China's Navy currently has no nuclear-powered aircraft carriers. The Liaoning, Shandong, and Fujian are all conventionally powered. If the Type 004 were to use nuclear power, it would represent an unprecedented systemic breakthrough. Even if it wasn't a thorium reactor but a traditional pressurized water reactor, the challenge would still be monumental. For a country that has never used a nuclear-powered aircraft carrier, jumping straight to molten salt reactors is radical and even risky. This approach carries not only high technical and management risks, but also significant public relations and strategic costs. Many people mistakenly believe that using a thorium molten salt reactor makes the Type 004 technologically advanced. In reality, the opposite is true. What if the cooling system is damaged? The reactor could freeze, and the entire power system could fail, rendering the ship inoperable. What if restarting the reactor takes too long? The enemy won't wait for the reactor to gradually heat up to 700 degrees Celsius. In the high-speed, high-pressure environment of naval combat, a molten salt system could end up being the fragile heart for the entire ship. 96 aircraft, the impossible triangle of space and efficiency. One of the core highlights in promotional videos for the Type 004 aircraft carrier is the claim that with a total of 96 aircraft, it will surpass the Ford-class limit of 90. The configuration list includes 60 J-35 stealth fighters, 12 unmanned attack drones, 8 electronic warfare aircraft, 6 early warning aircraft, 10 anti-submarine helicopters. It sounds incredibly powerful, and it certainly excites viewers, but where will these aircraft go? How will they get on and off the deck? How will they fit into the hangar? How much maintenance will be carried out, and how will they launch? An aircraft carrier is not just a place to park planes, it's a continuously operating, second-by-second scheduling, three-dimensional system. The flight deck acts as an airport runway and cannot simply be piled with aircraft. The hangar deck functions as a maintenance workshop, needing enough space for opening covers, lifting aircraft, and loading missiles. The elevators have a strict limit of how many planes can be moved up and down per hour. When a plane is repaired and ready to return to the deck, it needs to be taxied, positioned, the catapult must be free, and the hook calibrated. Everything must work in perfect synchronization. If any one step in the process gets delayed, it could paralyze the entire ship's scheduling. The more aircraft there are, the more conflicts, higher failure rates, and more complex scheduling there will be. Ford-class carrier versus Type 004. Space and capacity limitations. The U.S. Ford-class carrier has a full displacement of about 110 tons, with a hangar area of approximately 6,000 square meters and a flight deck area of about 1,800 square meters. It can accommodate around 70 to 75 aircraft, plus a few helicopters and early warning planes. Under maximum configuration, it can reach 90 aircraft, but that's a packed arrangement where the planes cannot be launched at high frequency. Even though the Type 004 is wider and larger, it can only increase usable space by about 10 to 15%, which is far from enough to accommodate the space redundancy required for 96 aircraft. Additional considerations include each J-35 fighter has a wingspan of 11.7 meters and a length of 17 meters. Maintenance stations, missile loading areas, and avionics maintenance racks will be needed. At least 1.5 to 2 times the aircraft's volume must be reserved for service space. It's not just about spreading the planes out, it's about carefully planning routes within the available space. Given these constraints, 80 aircraft are already close to the system's limit. While you can fit 96 aircraft, they won't be able to launch effectively. Aircraft elevators on a carrier are like subway transfer stations. No matter how many planes there are, has to be moved up and down individually. Ford class has 3 elevators, with a single cycle time of 2 to 3 minutes. The Fujian carrier has 2 elevators, with a theoretical capacity of about 40 to 50 aircraft movements per hour. In actual combat, due to scheduling and preparation time, the efficiency is only about 50 to 60% of the theoretical capacity. So that means even if the Type 004's elevators are enlarged and faster, it will still take several minutes of continuous scheduling to launch all aircraft at once. Packing 96 aircraft onto the carrier may result in planes that can't fit onto the elevators, blocking up the hangar. Planes that can make it to the deck but can't move around because of overcrowding. Repaired aircraft can't be moved because the elevators are already in use, leaving them waiting. And all of this is happening during combat operations. Some may say, why not just build more hangar space, make the hangar larger? The issue is that every square meter of hangar space is traded with displacement. The internal space on an aircraft carrier is already stretched to its limits. The power system requires space. The nuclear reactor or conventional boilers need a safety distance. The ammunition storage must be shockproof, heat-resistant, and explosion-proof. The crew dormitories, command center, fuel tanks, and cold chain supplies all need space too. Furthermore, modern aircraft have high maintenance requirements. The J-35 stealth coating requires separate maintenance space, with no mixing with other equipment. The avionics maintenance area needs to be anti-static and dust-proof. The missile loading area must be far from the heat sources and propulsion pipes. These are not static spaces, but dynamic surface areas. It's not enough to just fit the planes in. They have to be ready for use. The U.S. military has learned a crucial lesson from decades of aircraft carrier operations. Typically, 70 to 75 aircraft is the sweet spot, balancing mission scheduling, maintenance cycles, and logistics support. Once the number exceeds 90, the strain on maintenance manpower increases drastically. Deck scheduling becomes chaotic, and the elevator becomes a bottleneck. In actual combat, if a high-density sortie is needed, it's better to deploy 2 carriers in rotation than to create a giant ship with empty decks. Laser weapons and railguns, the brutal reality of power demands. The Type 004 will be equipped with a 200-kilowatt laser weapon, capable of melting through a missile 20 kilometers away in just 3 seconds. It'll have an electromagnetic railgun, capable of striking targets 300 kilometers away at Mach 7. In fact, the US has been working on these weapons for over a decade, but has yet to officially deploy them on any aircraft carrier. China, too, has never publicly tested the ability to deploy such equipment on a carrier platform. A 200-kilowatt laser with an efficiency of 30 to 40% would require an input of 500 to 700 kilowatts of power, and instantly expel more than 300 kilowatts of waste heat. This is even harder than cooling the carrier's main engines. If the seawater cooling system gets blocked, it can instantly cause a thermal shock. A single overload at high temperatures could require replacing the optical mirrors, and this is just one laser gun. What if the ship was equipped with multiple? The electromagnetic railgun was once considered the U.S. Navy's weapon of the future. It had impressive design goals, a launch speed of Mach 7, a range of 200 to 300 kilometers, and kinetic projectiles, no explosives, just sheer speed to penetrate the target. In 2021, the U.S. Navy officially terminated the railgun project for 3 reasons. 1. The 10-kilogram projectile traveling at Mach 7 generates around 28 megajoules of kinetic energy. The railgun operates at 30 to 40% efficiency, meaning it needs around 90 megajoules of input energy. If the firing time is 0.01 seconds, the instantaneous power required is 9 gigawatts. That's equivalent to 40 to 50 aircraft carriers generating power simultaneously. A Ford-class carrier's full power output is only 600 megawatts, which is only enough to feed 1/15 of the railgun's power demand. The energy storage system would need to be more than 10 times larger than the one required for electromagnetic catapults. Not even a medium-sized nuclear power plant could handle that. The result would be system shutdowns. What will the Type 004 aircraft carrier really be like? Maybe the design needs to come back down to Earth.